right, guys. So in this lesson, we're still looking at 4-1, but we want to talk about the different K values. So the different equilibrium constants, the more specific ones. So if you just say K, that means the equilibrium constant with respect to molarities. If you say Kp, that means the equilibrium constant with respect to partial pressures at equilibrium. But if you say KSP or KW or KA or KB, they're still equilibrium constants and they're all with respect to equilibrium molarities, but they describe a particular type of of reaction. Okay, it could be a chemical reaction if it's acid base, or it could be a physical reaction if we're talking about salt dissolving in water. Okay, so they describe a particular process, just like delta H of vaporization describes the chemical equation of vaporization, right? Or the delta H of formation, that specific subscript represents the chemical equation that shows 1 mole of a compound being formed from its elements. So KSP describes a particular type of equation. Ka describes a particular type of equation. All right, and that's what we want to get into in today's lesson. All right. All right. So again, right, all these Ks are basically the same exact thing except for Kp. Okay, but all of these are the same exact way to write them. You do products over reactants, coefficients become exponents, don't use solids, don't use liquids, use bracket notation because it's all about equilibrium molarities. Okay, but let's understand that these right here, those four, represent a specific type of equation. Right? These are all generic. The EQ there is just to remind you that it might be the equilibrium constant, and Kc is to remind you that, hey, it's respect to concentration. You're not always given that, okay? But Ka, specific type of reaction. Guess what? It involves an acid. Kp, specific type of reaction. Guess what? It describes a base. Kw, guess what? Water, okay? And then Sp, that's a little bit different. That's what we're going to be talking about first, okay? All right, so let's dive into it. All right. All right, so again, all these Ks and even these specific ones are with respect to equilibrium molarities. Okay, the only K that's different in that regard is Kp, and that's equilibrium partial pressures. Okay. All right, but these particular subscripts, the W, the A, the B, the Sp, describe a particular type of reaction. Okay. Okay. So the first one we're going to do is KSP because that's one we're really going to focus on in this unit, in Unit 4. Okay, when we get to 4-4, it's all about KSP. All right. Unit 5 will be all about Ka and Kb and Kw because that's acid-base chemistry. All right. So KSP. All right. The SP stands for the solubility product. So if you're asked for the solubility product, you're asked for the KSP. All right. So this describes the solubility of the number describes the solubility of a salt, of an ionic compound in water. And so the reaction that the KSP describes is it's not a chemical reaction, it's a physical change, but it shows solid salt dissolving into aqueous ions. That's the particular reaction. So let me show you what I mean by that. If I tell you the KSP for silver chloride is 1.6 times 10 to the negative 10. Notice that's a small number, and that's kind of telling us that silver chloride is not very soluble in water. And we already know that based on solubility rules, but this is kind of telling us how insoluble it is. All right. Now, if I want to show this salt dissolving in water, that chemical equation would look like this. All right. So solid AgCl breaks up into Ag plus aqueous and Cl minus aqueous. All right. So the equilibrium constant for this reaction, because it's showing the salt dissolving in water, that K is actually a KSP. All right? You could just call it K, but understand that this would be the KSP for silver chloride. Now, how would we get the expression for the KSP? Well, this is the reaction, so the expression would be products over reactants, coefficients become exponents, don't include solids or liquids. But for KSP, you're only ever going to have one reactant, and it's always going to be solid. So KSP expressions never have a denominator. It's just going to be this ion times that ion, but every once in a while, the ions will have a different coefficient other than 1, so you have to remember to square it or to cube it or something. But in this case, since that subscript is 1 and that subscript's 1, KSP, the expression, would be equal to the concentration of silver times the concentration of chloride. And because we were told what the KSP value was, we know that that expression is equal to that number. Okay? So what would the KSP expression look like for calcium chloride? Well, let's write the reaction. All right? Calcium chloride solid yields 1 calcium ion, but it yields 2 chloride ions. These would be aqueous. So the equilibrium expression, KSP, for this salt would be the concentration of calcium times the concentration of chloride squared. Don't forget to square it because of that coefficient there. And if the KSP, if we were told, was that, then that would be the equilibrium constant for this reaction at that temperature. And so that's what this expression would be equal to. Okay? But it's always a salt dissolving in water. All right? So what's KW? KW is very specific. It's only for water. And so it's only equal to one expression. But we can kind of show it 2 different ways. So, all right. It's good to know that KW equals 1 times 10 to the negative 14 at 25 degrees Celsius. This is where all of our pH equations come from, our pOH equations come from. pH plus pOH always equals 14. This is where this is coming from, okay? So what's the auto ionization of water? It's water breaking up into H plus and OH minus. So if this is the equation, then this is what the KW expression would be. Notice I'm not including a denominator because our only reactant is liquid and we don't include that. All right, so this equals that. Okay, that's what KW is equal to. But sometimes we don't like to show H plus and OH minus, so you could show 2 water molecules breaking up into hydronium and hydroxide, and then you get this expression. But remember, we've already been over this. In acid-base chemistry, H plus and hydronium are synonymous. So you're either showing KW this way or you're showing KW this way, but since H plus and hydronium are the same thing, there's no difference between this expression and this expression. It's just, what are you showing? Are you showing 1 water molecule breaking up into H plus and OH minus, or are you showing 2 water molecules bumping into each other and one of them losing an H plus to become hydroxide and the other one gaining the H plus to becoming hydronium? It doesn't matter, all right? But that's what KW is, right? Now, this constant's on your formula sheet, but you probably should memorize it. It's not that difficult, right? All right, so let's talk about Ka, all right? Ka is the acid dissociation constant, okay? And the equation that it represents is an acid acting like an acid with water in particular. So understanding what acting like an acid means. It means forming H plus in water, or I think the better way moving forward to think about it is an acid gives an H plus to water, so the water turns into hydronium, H3O plus, all right? But if you want to simplify it, right, if I'm told the Ka for hydrofluoric acid is 6.6 times 10 to the negative 4, then I'm given the equilibrium constant for this particular reaction. HF acting like an acid in water, okay? So how does HF act like an acid in water? It dissociates and forms H plus and F minus, okay? Now, the better way to think about it, it doesn't matter, it's the same exact thing, okay, would be showing HF giving an H plus to a water molecule so you get hydronium and you get fluoride, okay? This equation and this equation are equal to each other. That K and that K are the same exact thing. It's the Ka for this acid, okay? The expressions look slightly different, but because, remember, we don't use water, right? We don't use liquid in our expression. Notice they're basically the same thing. H plus times F minus over HF, or hydronium times F minus over HF. Same thing, all right? So Kas show an acid giving an H plus to water, okay? And so if that's the equation, then I can write the expression that the Ka equals. So if that's my equation, then this is the Ka expression. And I know what Ka is equal to because they told me that. So I know that this expression equals that number. Okay. All right, well, what about Kb? All right, well, that's base dissociation. It shows a base acting like a base with water. It has to be with water. What does acting like a base mean? Acting like a base means taking an H plus away from water. If you take an H plus away from water, what are you left with? Hydroxide. Okay? So if I want to show ammonia acting like a base with water, okay, I would say ammonia plus water. I would give an H plus from the water to the ammonia. That would become ammonium. Okay. And then the water would become hydroxide. All right. So if I'm told the Kb for ammonia is this, then I know that this K, this Kb value, is the K value, the equilibrium constant value for this reaction at whatever temperature we're talking about. And I know that this value would be equal to this expression because this would be the equilibrium expression for this equation, right? Products over reactants, coefficients become exponents, don't include liquids or solids, right? So this times this over that, all the coefficients are 1, so I have no exponents. So that's what it would be, all right? So let's do some practice. Write the KSP expression for ammonium phosphate. Well, if it helps, write the equation that describes KSP. So I would show the salt dissolving in water because I'm concerning KSP. So that's the equation. So really, if I'm asked this, it's really, hey, write the equilibrium constant expression for this reaction. So products over reactants, coefficients become exponents, don't use solids. So it would be the ammonium concentration cubed times the phosphate ion concentration. And it wouldn't be over anything because our only reactant is a solid, and I don't include that in the expression. Okay? All right. Well, what if I wanted to write the Ka expression for HCN? Well, write the equation that should describe. Kas are acids acting like an acid with water. So show HCN and water. Acting like an acid means the HCN loses that H plus to the water, and you become hydronium. And what's left if this loses an H plus? Cyanide. So that would be the reaction. And then from that reaction, we would just write the equilibrium expression. So this times this over that. And again, I'm not including the water in the expression because it's a liquid. Okay. Well, what if I wanted the Kb expression for this? Well, if I'm looking for a Kb expression, then that must mean this is a base. So you need to show this acting like a base in water. What is acting like a base in water? Gain an H plus from water. Okay? And it really doesn't matter. If you don't know where to put the extra H here, you could put it right here. Just as long as you understand, you're not just gaining an H, you're gaining an H plus. So if this is neutral over here and it gains an H plus, then it's plus 1 over here. All right? So you would show this plus water, okay? Acting like a base means it takes an H plus away from water. So again, you don't have to throw that. So notice I have NH2 here and I made it NH3. You could have just added an extra H over here, or you could have accidentally added it to here. That's fine. It doesn't matter. Just as long as you know you have an extra H in this equation. And now that it's plus 1 because it wasn't just an H you gained, it was an H plus. And then the water becomes hydroxide after it loses an H plus. All right, so that's the equation that would describe this as a base. So the expression would be this, it would be Kb equals this times this over that, and I'm not including the water, okay? So again, it doesn't matter what I tell you is a base, all right? Right? If I just say, hey, this is a base, show it acting like a base in water. Write the word base. Right? Then take an H plus away from the water and add it to the base. So base turns into H base plus, okay? Because assuming this was started out as neutral, right? And then what are you left with? OH minus, okay? For an acid, right? It doesn't matter what the acid is, just write the word acid, right? the acid has to have, for an acid to act like an acid, it has to have at least one free H plus to give. So H acid plus water yields just the acid minus by itself because it lost its H plus to water, and then you have hydronium, right? And remember, that should look familiar to you, right? What's this? This is the net ionic equation for a weak acid acting like an acid with water. Okay? Right? It looks very familiar to this. Just instead of acid, A. HA, A minus. H acid, acid minus. All right? Same deal. All right? It's really easy. Acting like an acid with water means I lose an H plus to water. Acting like a base with water means I take an H plus away from water. If I lose an H plus, my charge decreases by 1. If I gain an H plus, my charge increases by 1. That's it. All right. So hopefully that clears it up. When you get that particular subscript for a K, it describes a particular type of reaction. All right. And you want to know what type of reaction it describes. Okay. So we'll spend a lot of time on KSP when we get to 4-4. But KAs and KBs, they're going to come back with a vengeance when we get to Unit 5 and we're doing acid-base equilibrium, acid-base chemistry. Okay. So, they're not going away. All right. All right. So hopefully that helps.